Alright guys, so if you look into the story that of DFT that we have been considering in our previous discussion, it ended up in a bit of an anticlimactic way. We had a specific purpose for DFT, and that purpose essentially was to identify the stable configuration of the atom. In the first place, we are interested in stable configuration of the atom is because each stable configuration or each configuration of the atoms, it pertains to a phase in a material system. So when I'm able to say that for a given condition, this is my stable configuration, what I essentially mean by that is, for a given condition, this phase of my material is going to be stable. So ultimately, when I'm able to extrapolate my present observation of DFT, it means that I will be able to build an entire phase diagram from it. I don't have to worry about doing different experiments. All I have to do is perform several DFT calculations. At the end of it, I should be able to build a phase diagram. But unfortunately, we realize that the different expressions that come in the formulation of the DFT theory, or DFT calculations rather, they fail to include the effect of temperature. So in our discussion, whatever we have considered the different aspects of DFT, the effect of temperature was not explicitly factored in. So it in principle means that whatever structure that we find stable through DFT calculation, it is for absolute zero condition. It is stable for absolute zero condition, and when you move away from the absolute zero condition, the stability of the phase or the structure or the configuration is prone to change. Now when you consider the phase diagram, and particularly when you are interested in knowing which phase is going to be stable at different conditions, one of the different conditions that we are interested in is varying temperature. So DFT as it stands will not be able to help you with identifying or building the phase diagram. So alternatively, the way now forward is to somehow introduce the effect of temperature and ensure that we are able to make the utmost use of our DFT calculation. That means that we are able to come up with the phase diagram from DFT calculations. So in order to do that, one approach could be that we include the effect of temperature directly into ascertaining the wave function, or we can include the effect of temperature in formulating our Hamiltonian, thereby directly introducing the effect of temperature in the wave function, and so on and so forth. So that is one way of going about, meaning from the foundation level, you change the entire formulation of DFT, thereby you are able to introduce the effect of different temperature. You are not just confined to the absolute zero. Or we can rather bring in another domain into this DFT calculation, and thereby enabling us to introduce the effect of temperature. What I mean by that is, when we talk about phase diagram, the one aspect of materials research or one aspect of materials domain that helps us build this phase diagram is thermodynamics. So it should be possible for us, an alternate should be rather bringing in the concept of thermodynamics in the framework of DFT so as to get the stable energy configurations at different temperature. So we have two routes. One is foundationally introducing the effect of temperature from the foundational aspect of DFT, or the other alternate is bringing in some understanding, some concepts of thermodynamics in the DFT framework, thereby allowing us to determine the effect of temperature at all the stability of different configuration, or to put it even more simply, to understand how the stability of the configuration is going to change with increase in temperature or as we move away from absolute zero. In order to do that, again, we are planning to bring in the concepts of thermodynamics. And one primary concept that we need is the concept of free energy, because it is based on the free energy that we are going to say which of the two phases is going to be stable. When you ignore all the DFT discussions that we had so far, when you take the material or when you take a system, and when you understand, or when you are want to understand rather the stability of the system under a given condition, what you essentially would find out is the free energy of the system, and depending on which of its states assumes the lowest free energy, you will say that this state is going to be the stable state. Now essentially that is what we are going to do when we want to understand or introduce the effect of temperature in DFT in this case. So there are several ways to do it. One way is to introduce the concept of free energy or thermodynamics. By means of thermodynamics, we are introducing the concept of free energy to help us identify which is the stable configuration. Now, in this formulation of the free energy that is based on DFT, the term E0, which is there in this formulation, it is nothing but the ground state energy that we calculate from the DFT calculation. This term E0 is something that stems out of our DFT calculation, and it pertains to our 0 Kelvin. Now, in order to bring in the effect of temperature, we are adding two additional contributions to our free energy of the system. So we have a configuration, and we want to find if this configuration is going to be stable at high temperature or not, or how with temperature the stability of this configuration is changing. In order to do that, we are calculating the free energy of this configuration, and the free energy of this configuration includes three parts. One is the ground energy state that we calculate from our DFT, and these are the other two terms that contribute to the free energy of that configuration. So we have a major contribution from free DFT. We have other two contributions that will add to the existing configuration, thereby enabling us to say if this configuration will be stable at high temperature or not, how the stability is changing with temperature. Now, the first contribution involves, so it means it involves electrons. So that is all we can know about this just by looking at it. And this is vibe, so it means it talks about not other vibes, it talks about the vibration. So essentially what we have is, we are bringing in the effect of high temperature through two free energies. One free energy, it talks about, or it includes, or it accounts for the vibrations of the atoms. So you have your elastic vibrations of the atoms and the free energy change that is introduced by the elastic vibration of the atoms, or the contribution to the free energy by this vibration is brought about by this term here. Then this term here, it talks about how the different energy levels of the electrons are occupied as you vary the temperature. Again, just to reiterate, we are trying to identify the effect of temperature on the energy of the system founded on DFT. So the foundation on DFT comes from E0, but E0 doesn't have any effect on temperature, or temperature is not involved in the calculation of E0 because it's for absolute zero. So we need to include the contribution of temperature. The way we include the contribution of temperature is, one, by considering the vibration of the atoms as that is introduced as you increase the temperature. The other is the occupation of electrons, at different energy levels as you increase the temperature. So my increase in temperature is going to affect my system in different ways, going to affect my material in different ways, but I'm considering two factors. One effect is the vibration of the atom, the other effect is the occupation of electrons at different energy levels. So since the occupation of electrons at different energy levels is influenced by the temperature, and also since the amount of vibration or the vibration of the atom depends on temperature, by introducing these two contributions, I'm able to now calculate my free energy of my system based on my DFT that is dependent on my temperature. So my free energy calculation is foundation, it stems from my ground state energy, and to that I'm adding two contributions. These two contributions are dependent on temperature, so ultimately the free energy that I calculate is also dependent on temperature. So now when I determine or estimate my stability based on this free energy, this extended free energy, instead of my E0, then I have a parameter that would help me understand the stability of my configuration with respect to my temperature. So that is the idea behind it. So instead of changing the entire formulation from the foundation up, what we are doing is we are introducing a new parameter. We are taking a different approach of estimating the free energy of my configuration, and this formulation of the free energy is having two new terms that are dependent on temperature, so thereby ultimately influencing my estimation of free energy. And we just saw what these two new terms are. Now, even though this appears to be rather an elegant approach, there is of course an approximations that we are making. We are assuming that there is no interaction between the electron and phonon. So what we mean by phonon in this case is, Once your atom begins to vibrate, it introduces a wave into the system. So there is this energy wave that is introduced into the system because of the elastic vibration of this atom. Now this wave, the energy of this wave can be quantified as, can be viewed as a particle. This wave that is introduced in the system can be viewed as the particles, and the energy can be quantified as the quanta of particles, and that is what we mean by phonon. So phonon are nothing but this quanta of energy that is associated with the wave that is introduced by the vibration of the atoms, and that is what we mean by phonon. The quanta of energy associated with the vibration of the atoms is what we mean by phonon. Of course, like we view electrons as both particles and waves, of course phonon that stems from, or that gets introduced by the vibration of the atoms and the resulting wave, can also be viewed as a particle, that is the quantum, particle with the quantum of energy. So what we assume in this formulation is there is no interaction between electron and the phonon that is associated with, or that results from the vibration of the atoms. Now, having made that assumption and having brought in the effect of temperature through two free energies, we will see how we are estimating these two free energies. So let us begin by considering one free energy that stems rather from the occupation of electrons at different energy levels. So we are calculating one free energy that stems from occupation of electrons at different energy levels. Again, this occupation of electrons at different energy levels is going to be dependent on temperature. As I increase my temperature, my electrons are going to gain appropriate energies, and they are going to occupy different levels, and the free energy associated with this occupation is what we are going to formulate, and this is the way we are formulating this. So the free energy of the electrons with respect to temperature, depending on which energy levels they occupy, is expressed in this way. Now, first thing we need to notice here is we are rather ignoring this term here. We are subtracting this term here. So this term essentially talks about the energy of the electrons at absolute zero. So we have a formulation for the free energy of the electrons depending on their occupancy at a given at different energy levels pertaining to a given temperature, and in that formulation we are ignoring the energy of the electrons at 0 Kelvin. The reason we are ignoring the energy of the electrons at 0 Kelvin in this formulation is because we have considered the ground state energy at 0 Kelvin in the original formulation. So if we include it in this as well, so if we don't remove the energy of the electrons at 0 Kelvin, it means we are including it twice. So since we already have a ground state energy formulation, we already have a ground state energy emerging from DFT calculation, so when we are formulating our free energy of the electron based on temperature, we are ignoring, or we are removing, the energy of the electrons at 0 Kelvin. So having removed that, we have two terms that we have to account for. One term and the other term that we have to account for. This term is referred to as the band energy of electrons. This, the first term, is referred to as the band energy of electrons. So what band energy of the electrons means is that when we have electrons in a single atom, they occupy specific shells. When you consider a single atom and we can consider the electronic configuration within that single atoms, the electron occupy specific shells, and each of these shells have energies, specific energies associated with them. So it means the electron within an atom, they occupy specific energy levels in the form of the shells. Now, instead of a single atom, if you bring in several atoms together to form a system, to form a continuum, it means that you are going to establish electron cloud, particularly if your electrons pertain to a metal, meaning your atom is electropositive in nature. So when you bring a set of atoms that are electropositive, that are inherently electropositive in nature, let's say you are trying to build a block of metal, you are bringing in several atoms, and each of these atoms are going to contribute to your electron cloud. And now the electrons in the electron cloud, they are going to occupy specific electron levels. So you are bringing in atoms, and these atoms are going to contribute to the common electron cloud. And when you have large number of atoms, correspondingly the number of electrons in your electron cloud is going to increase, and these atoms are going to occupy different positions, or they are going to occupy different energy levels. So when there are numerous electrons, instead of having individual energy levels, what you will be ending up having is energy bands. So instead of having individual energy levels as in atoms, you will have several combinations of levels, thereby ending up with energy bands. Now, depending on the temperature, the number of atoms that occupy a given energy is going to vary. Depending on the temperature, the number of electrons rather that occupy a given energy in this energy band is going to vary. So what band energy helps us understand is, it helps us calculate the overall energy of my electrons by considering the different energy levels my electrons occupy. So I'm going to form an energy band because I'm considering not just one electron but a cloud of electrons. The cloud of electrons are going to occupy different levels in this band. My overall band energy now is nothing but the product of the energy level and number of electrons that occupy this energy level. So if I have an energy level, say epsilon I, the number of electrons that occupy this energy level epsilon I, if I assume it to be Ni, the summation of I ranging from 1 to, let's say, a large number n is going to be my band energy. So that is how I would rather easily formulate my band energy. I have number of electrons occupying a given energy level. I consider all the energy level in my band, sum it all together up, I come up with my band energy. Now, when my temperature is changing, the number of atoms or electrons rather occupying a given energy is going to change, correspondingly by changing my band energy. So that is how I will essentially estimate my band energy. Now, since my energy levels are continuous, I have to replace my summation. I can replace my summation with the integration. So I will have an integration with respect to my different energy levels and their corresponding energy and the electrons associated with it. So if I integrate this, then I will be able to calculate my band energy. I started off with individual levels. Now, since my levels all combine to form the band, a continuous band, I use instead of summation and integration. Now, this is rather the foundation of the expression for the band energy that we are about to see. Remember, it's nothing but we are integrating our energy with respect to the atoms that are associated or electrons that are associated with a specific energy, and we are considering a wide range of energies of the energy band. We are considering a specific energy, number of electrons associated with a specific energy, and we are considering the entire band. So ultimately that will give us the band energy here. So this understanding of band energy can be expanded as something like this. So what we have conceptually understood the band energy as, it can be expressed in this way. Again, you see the energy epsilon that we talked about associated with each of the levels is included here, and we are integrating over the entire band. Now there are two new terms here that we have to account for, but if you recollect our previous understanding or previous discussion, the combination of this f of epsilon and g of epsilon should ultimately yield n, which is nothing but the number of electrons that are associated with my energy epsilon. Before getting into this extensive representation of my band energy, we had a conceptual understanding. That conceptual understanding was, within this integral there needs to be the product of number of electrons and the corresponding energy. If you take that conceptual understanding, place it in here, I have my epsilon already present, but in addition to that I have two other terms. So what it means is, these two other terms, they should represent the number of electrons associated with the energy, and that is exactly what these two other terms do. The first term here, we refer to it as the Fermi distribution. So what Fermi distribution talks about is, so this is the expander, or this is the formulation for the Fermi distribution. So what it talks about is the probability of finding an electron, or for probability of an electron assuming a specific energy. So my Fermi distribution is nothing but the probability of an electron assuming a specific energy, and that energy is epsilon, and this mu is a constant, and this is referred to as electronic chemical potential, but it's a constant for a given configuration at a given temperature. So it is nothing but how the energy changes if I remove or add an electron. So this is a constant, this is my energy that I am interested in. So this term here tells me what is the probability of an electron assuming a given energy at a given temperature T. Now this is the electronic density of states. So this term G of epsilon is nothing but the electronic density of states. So what it means is that different energy levels within a band, they have several states associated with them. If I take the ratio of number of states associated with a given band, it gives me the density of the states. So what I'm essentially doing is, to put the matter simply, I have different levels that constitute my energy bands. These different levels have different vacancy. The ratio of these vacancy with respect to the F energy level is going to be my electronic density of states. So this vacancy, the so-called vacancy, the term vacancy I just introduced to help you understand, this term vacancy is nothing but the different states within an energy level, and in these states the electrons can occupy. So when there are numerous states within a given energy level, numerous electrons can occupy that states, thereby presenting themselves at the same energy level. So what G of epsilon states is how many, so simply put, how many electrons a given energy can accommodate. What F of epsilon says is what is the probability of an electron at a given temperature T to reach that energy, to assume that energy. So one talks about the number of electrons a given energy level can accommodate. The other talks about the probability of an electron assuming that energy level. So the combination of these two gives you the number of electrons, the possible number of electrons at that energy level, and the combination of these two, the possible number of electrons and the energy associated with that level, the combination of these two and integrated over the entire band will give you what we refer to as the band energy. So it is rather possible for us, even though it looks rather difficult, it is possible for us to comprehend this expression here. So I hope you understand what band energy is. Now the other term is a bit more tricky because entropy, the term entropy is always tricky. So what we are now trying to find is, we are trying to find something called as electronic entropy. So what essentially we are trying to do here is what we are doing here is some aspects of quantum thermodynamics. Now, of course, if you consider classical thermodynamics, your system is going to be macroscopic in nature. If you consider statistical thermodynamics, of course, you are going to involve atoms in it. Now, what we are doing is quantum thermodynamics because we are dealing with electrons and entropy of electrons and so on and so forth. So here, this term, it talks about electronic entropy or entropy of electrons, and the way we describe it is something like this. So this is how we describe the electronic entropy. Now, of course, this expression can be intimidating, but if you recollect that combination of this term and this term is nothing but a combination of F of epsilon and G of epsilon. So F of epsilon, of course, I'm ignoring these constants here. So F of epsilon and G of epsilon is the number of electrons. It's number of electrons. I can, of course, rewrite it as something like this: n ln of n plus 1 minus n ln of 1 minus n. Now, if you have considered or if you have looked into any textbooks on thermodynamics, so this is how you essentially describe your configurational entropy in a system. So in the classical thermodynamics, in the sense of classical thermodynamics, when we want to consider configurational entropy, of course, apart from the degree of irreversibility, if you want to describe your configurational entropy, this is how we would define it. So the same description is being extended here. So using our understanding from, or based on the understanding of entropy in the classical thermodynamics, now we are able to describe our electronic entropy rather. So we were able to make sense of band energy, and we were also in a sense able to reason out why this is the formulation of the electronic entropy, because it stems from our classical description of configurational entropy. Now this gives an account for our free energy contribution from the electrons. Now we have to account for the free energy contribution from our vibration. So if you consider the free energy contribution from the vibration, it is expressed in this way. Of course, there are few parameters that we are kind of aware of. One is the Boltzmann constant, so that we are aware of this. Of course, the temperature is involved, we are aware of this, and we have the Planck's constant. Now there is a sign h here, is primarily because we are assuming that our vibration is harmonic in nature. So because our vibration is harmonic in nature, we have this function included. So only one parameter that we have to be absolutely sure is the parameter nu. So this nu essentially talks about the frequency of the vibration. So now if you are able to introduce or estimate the frequency of the vibration, then lo and behold, you will be able to calculate the free energy contribution from the vibration of the atoms. In order to calculate this vibration on this frequency, and this frequency essentially dictates this G of nu, which is nothing but our density of states that pertains to the density of states that pertains to phonon or vibration. So the density of states that pertains to the vibration. So this again depends on mu, the frequency. So ultimately, if I'm able to come up with an expression for frequency, or if I'm able to identify the frequency, then I'll be able to find the contribution to my free energy based on the vibration. Now, in order to do that, we begin by estimating the force that contributes to, or that induces this, or that rather propels this vibration. So this force is a tensor, and it is expressed in this way. So we are talking about a force tensor that propels the vibration, and that is expressed in this way. And this force is nothing but the derivative, the double derivative of U, that is the potential energy, with respect to the displacement of atom I and atom J in directions alpha and beta. So what we are considering is, we are considering pairwise vibrations of the atom and how the potential energy is changing when these pairs of atoms are vibrating. So we are considering change in the potential energy while the pairs of atoms are vibrating, while the pairs of atoms are getting displaced. So we are considering change in the potential energy with respect to change in or the displacement of the atom I and the displacement of the atom J in direction alpha and beta. So alpha and beta, they can assume the value of x, y and z. So we are considering the pairwise movement of the atoms I and J. So the I and J, these terms I and J, they indicate different pairs of atoms. So they can never be I and I, so they indicate different pairs of atoms. And alpha, beta, they indicate the different directions. So it can be xx, it can be xy. So we are considering all the three principal directions, the displacements along all the three principal directions. So when we are able to estimate the change in the potential energy as my pairs of atoms are displacing themselves in two different directions, based on that we are able to come up with the tensor, the force tensor. Now, when I'm considering a system that comprises of n particles, and I have to consider all the pairs of the n particles, then when I want to represent all these forces that comes from, so this force is rather, it emerges from the pairwise consideration. So this force that I'm estimating, this tensor force that I'm estimating, it comes from pairwise consideration. So I'm considering pairs of atoms I and J. So based on that pair, I'm calculating this force here. So if I want to include all the pairs of my n atoms that is present in my continuum, that is present in my material, then the way I represent my tensor is, what I ultimately end up having is a dynamic matrix like this. So what this dynamic matrix involves is rather, this dynamic matrix, it talks about the force vectors, these force tensors with respect to all the pairs of atoms that are possible. We are talking about n different atoms and all the pairs of the n different atoms and the force tensor associated with them, and that we are representing in the form of this dynamic matrix. So this term, it just talks about interaction between atom 1 and atom 2. It talks about interaction between atom 1 and atom 3 and so on and so forth. Now when I consider when I want to include or represent the force between all the pairs of atoms that is available in my system of n atoms, I can represent it in the form of this dynamic matrix. And the eigen value of this dynamic matrix is nothing but our frequency nu. So when I'm able to formulate this dynamic matrix and I'm able to find the eigenvalue of it, I'll be able to find its frequency. So ultimately now I have a framework to calculate my frequency. I also have my framework to calculate my band energy. So the band energy is going to be dependent on temperature. My frequency is going to depend on temperature, and ultimately this guy is going to dependent. The free energy associated with vibration is going to be dependent on temperature. So ultimately, the two contributions that I've included is going to be dependent on temperature. So through this contribution, my free energy is going to be dependent on temperature. The free energy that is founded on DFT is going to be dependent on temperature, and using this, I'll be able to say which of this configuration is going to be stable at any temperature. So ultimately, my limitation of DFT to a specific temperature, that is absolute zero, is now being relaxed by using a different formulation, by rather estimating the free energy of a given configuration that is founded on my ground energy or ground state energy. It still is founded on my ground state energy, this guy here, ground state energy, but I'm just including the contributions of two terms that are influenced by the temperature, and through these two terms now I'm able to say which of this configuration is going to be stable at any given temperature. So with this, we are rather winding up our story on DFT. We had a wonderful foundational story for DFT. We reached roadblock, and now we have even surpassed that roadblock by a different formulation. With this, we will wind up our discussion on DFT, and possibly we will resume our discussion on tensors in the next one. Take care, guys. Goodbye.